Hi, I'm Daniel Chan from UNSW Sydney. Welcome to another adventure in pure mathematics. In the classical Galois theory of finite field extensions, only finite Galois groups can arise. Now, if you want to study infinite field extensions, you will get some infinite groups arising, and the types of infinite groups that you can get are rather special. They're called profinite groups, and that's the subject of this video. Now, this is something that hopefully you've seen an example of before, and usually the first example that someone meets of a profinite group is the additive group of p-adic numbers, and that's going to be an example that I'll talk a little bit about today as well. Okay, so let's see how we get profinite groups. It's a constructive procedure, and the input that we need is what's called an inverse system of groups. So let's see what that is. So firstly, we need a whole set of groups, and we need an indexing set for that. And that's going to be not just a set A, it's going to be a poset. So we'll partially order this, say with this relation here, this partial order here. And this partial order has to be directed in the following sense, that any two elements, alpha, beta, in this set A, has to have some upper bound. Let's say some gamma upper bound, just meaning that it's greater than or equal to alpha and beta with respect to this partial order. So for each of the indices, alpha inside A, you want to have a group. Okay, and where does the relation here, this partial order, come in? Well, not only do you need to have these groups, but also if you have a relation of this form, if alpha is greater than or equal to beta, then you want a group homomorphism from G alpha to G beta. Okay, so that's the data that you need. So basically an indexing set. For each index, you'll have some group. And if you have two groups which are related, okay, like this, then there's a corresponding group homomorphism. And you want these group homomorphisms to be compatible with each other. So what does that mean? So suppose if you have alpha is greater than or equal to beta, and beta is greater than or equal to some gamma, so there's that means that there'll be a map from G beta to G gamma. In that case, if you'll also have alpha is greater than or equal to gamma, so if you go directly from G alpha to G gamma via phi alpha gamma, that's the same as if you go from G alpha to G beta via phi alpha beta, and then G beta to G gamma via phi beta gamma. So that's the natural sort of compatibility condition that you would want in such a setup. So if you have this data, you have an inverse system of groups. So let's look at some simple examples. The first one here is the one that's going to give rise to p-adic numbers, and we start by fixing some p, which is a prime. So indexing set, we're going to index this with the natural numbers, and the partial order is just the usual less than or equal to that you have. Okay. And what are the groups? The groups here, basically when you want to look at p-adic numbers, the idea is that you want to consider integers modulo higher and higher powers of primes. Okay, so you're focusing on some prime, and you want to see what's happening modulo high powers of this prime, okay, but arbitrarily high powers of this prime. So that means that you want to consider all z mod p to the n for all n natural number. Okay, so what's the map that goes in between them? So if you have n is bigger than m, okay, that means that Pn is not only just bigger than Pm, but Pm is a factor of Pn. So you have a natural map from z mod Pn to z mod Pm. Okay, what's the natural quotient here? Well, basically you take a coset containing A to the coset containing A. Okay, and that's well defined because if you change this representative A by some power of Pn, and some multiple of Pn rather, that multiple of Pn, of course, since n is greater than or equal to m, is certainly a multiple of Pm, and so it doesn't change this coset here either. Okay, so this is well defined, and just the way you see, it's quite easy that this condition holds. So basically, this is just saying coset of A goes to coset of A, and so if you send coset of A to coset of A, and that coset of A gets into coset of A, of course you get this compatibility condition holding. Okay, so that's quite easy, and that's an important example. Let's look at a slightly different example where again the indexing set will be the natural numbers, but this relationship here is given by divisibility. So m is less than or equal to n if and only if m divides n. And this time we're not fixing any prime, but you want to look at modulo arithmetic modulo any integer that's given by this index n set. So Gn equals Z mod n. In this case, you get a phi n m whenever n is a multiple of m, so Z mod n maps to Zm, and it's the same map here, and this is well defined for the same reason that it was here. Okay, if you change this by some, this A by some multiple of n, any multiple of n, since m divides it, is also a multiple of m, so it won't change this class here, and this is the natural quotient that you have. Okay, so this is a more complicated example because the poset here is a bit more complicated. Okay, but nevertheless, that's something that you can do to get an inverse system of groups. Okay, so that's the data that you need to get a profinite group, and let's see what we can do with this inverse system. So what we can do is called take the inverse limit of these. So the inverse limit of this inverse system above is the following. Okay, so what we're going to do is we're going to start with a very big group, which is just the product of all those G alphas. Okay, so this is something that you can form with this index at A and just these groups, but we haven't used these homomorphisms yet. So what we're going to do is we're going to take a subset of that. So this is going to be a subgroup of the product group here, and it's defined as follows. So it's a subgroup, so you're going to look at some tuples inside this product, but they have to satisfy this condition that I need to spell out for you. So what's that condition? And of course we need to use the group homomorphisms here. Okay, so what's that? So suppose we look at all the group homomorphisms, phi, alpha, beta. What you can do is you can apply this to the alpha component here, which is G alpha. And this has to be equal to the G beta. And this is for all alpha, beta. Okay. So you want to look at the subgroup of all such things. Okay. And in the special case where all these G alphas are finite, then we say this inverse limit, okay, which is this subgroup of this product, is profinite. Okay, so that's the definition of a profinite group. So it comes from a possibly infinite set of finite groups. So in particular, actually, it will turn out that every finite group will also be profinite. Okay, and you take this possibly infinite product and you look at this subgroup, and very often that will also be infinite. Okay, so there are certain types of infinite groups. Okay, I guess to check that it is a group, you do have to check that this is closed under multiplication and inverses, and it's quite easy to see that that's true. Okay, so suppose we want to invert this element here. Okay, so that means you invert all of these G alphas, and you want to show that this still satisfies this equation here. And the point is that these phi alpha betas are all homomorphisms, group homomorphisms, so they preserve inverses. So it sends G alpha inverse to the inverse of this G beta. Okay, so that means that when you invert this element, where you invert all of the components, okay, it still satisfies this condition. And similarly, if you take two tuples that satisfy this condition here, the product will also satisfy this, because homomorphisms preserves multiplication. Okay, and easily enough, you can check that if all of these are ones, the identity inside here, then this certainly holds. So that's the subgroup axioms that are checked. Okay, and so we have an example of a group, which is rather interesting. So let's see how that works in the examples that we've got of inverse systems here. So the first one is this one. That's going to give us the p-adics. Okay, so I claim that the limit of the Z mod Pn is Z hat P. Okay, and hopefully you can kind of see, depending on how you were taught the p-adic integers, that this is the case. This will be the additive group of that. If this is something that you've not seen before, let me give you a little example of how you can get elements inside here which are rather interesting. Okay, so one way to think about what are the elements inside here is you want to think of this as backwards based P. So you have, in fact, all power series in P where the coefficients of these powers of P are integers 0, 1, up to P minus 1. Okay, so I claim that any such power series, such as the one that we have here, 1 plus 2p plus 2b squared and so forth, that will give us an interesting element inside this inverse limit, this group of p-adic integers. Okay, so the first thing to note is that by the way I've enumerated it, you can see that this is an infinite group. Okay, that's the first thing. The other thing, I guess, is that you may think, well, if you have such a power series, how do you add them together? You just add them coefficient-wise, but sometimes if the coefficients add up to more than p, then you have to adjust the ones further down. Okay, so sometimes you have to do some shuffling that's involved here. Okay, but nevertheless, you can make that work, and it's not hard to think about why that works. There are some technical subtleties involved, but it's not difficult to see. But what I want to do here is to show you that how some power series like this actually gives you an element of this limit here. So the first thing is that what I need to do is I need to show you that this gives you an element in each of these groups. Okay, you get a tuple. Okay, you get a tuple, so for each alpha, so for each integer n, you get an element of z mod pn. Okay, so for example, if n equals 3, what's that element? So you're looking at z mod p cubed. Well, all the higher powers of p after p cubed, they will be going to 0. So if we interpret this as something in z mod p cubed, okay, you can think of them as all 0, and what you get is 1 plus 2p plus 2b squared. Okay, so the corresponding element inside z mod p squared will be, well, p squared will be going to 0, so it'll be just 1 plus 2p. Okay, and the point is that, well, you can see that for any n, you can get, well, possibly different integers that come up. Okay, but what's nice about this situation here is that this compatibility condition is very easy to hold. Let's just check it in the case where we have 3 and 2 are the numbers here. Okay, so how do we know that when we look at what happens in z mod p cubed, that's this integer here, okay, and we apply this homomorphism, you get this the coset of this integer here, and that's because, well, when you go from z mod p cubed to z mod p squared, basically you just look modulo p squared, and so a modulo p squared, 1 plus 2p and 2p squared is the same as 1 plus 2p. Okay, so you've got compatibility like that. So that means that these infinite power series, okay, they all give you elements of this p-adic integers. Okay, so this inverse limit of groups, and that shows you that in fact this is an infinite group, and you can hopefully see now that there are kind of some interesting elements inside there. Okay, so the next example that I have here, it's harder to write out what it is. Okay, it turns out actually that this will be, the notation is that it's written as a Z with a hat. Okay, so very often the hat is used to denote completion. Okay, and so that's why we use the hat. Also, the word profinite, it comes from the fact that we think of this limit as a limit where you go further and further back, you're pulling further and further back. And so we call it a projective limit, so hence the word profinite. Okay, so Z hat is a very, very important group in mathematics, and it's a very fundamental example of a profinite group. So what's really interesting about this profinite groups and what happens when you have this situation here is that you should, for profinite groups, you should think of them not just as a group, but actually as a topological group. Okay, so that means that it has a topology, and the topology is compatible with the group multiplication and the group inverse, in the sense that the group multiplication is continuous, as is the group inverse. So those maps, okay, so the group multiplication is a map from G cross G to G, and if you put topology on G, that means that G cross G also has a topology, so you want that multiplication map to be continuous. And the same with the inverse map from G to G, you want that to be continuous. And how do you do that? Okay, so the way to do it is very simple. Okay, so you consider a profinite group, G hat will be the inverse limit of these finite groups G alpha. So the first thing to do is that on each G alpha, you just put the discrete topology. Okay, so this is a finite set. It's a finite set, you can put a discrete topology on it. Okay, and since it's finite, actually this discrete topology will actually be compact. Okay, so that's actually a compact set. And what about on the product? If you look at the product, you can construct a product topology on that. Okay. So note one of the things that you can do with a product is that you have a projection homomorphism to any of its factors. And the topology that's given on this product is given by certain sub-basic open sets, which is just the inverse images of all the opens inside each of these G alphas. Okay, if you look at the inverse image of any open inside here, inside this whole thing here, in other words, you fix the that particular component to be inside a particular open set. Okay, that'll give you a sub-basic open set. So a basis consists of finite intersections of these. And finally, this G hat is a subset of this, so you can put the subspace topology on this G hat. Okay, so that's rather nice. You have this topology. And what's rather interesting here is that this G hat here for this profinite group is a compact topological group, and it has some interesting properties. So one of them is that, for example, what are its open subgroups? What are the subgroups which are also open as sets in the topological space? And they're the ones that turn out to be also closed and of finite index. Okay, so let me show you this. So if you haven't had much familiarity with topological groups, some of these arguments will hopefully be rather interesting for you, because the way the group structure and the topology interplay is rather interesting. Okay, so I guess the first thing that we want to show here before we do anything is I want to show you that G hat is actually closed inside this product. Okay, so to do that, I need to show you that the complement is open. So let's just find something that's not inside this G hat, so some tuple G alpha that's not inside this G hat, and we show that we can find some open neighborhood of it which is disjoint from this G hat. Okay, so that means that the complement, that will show you that the complement of G hat inside this product is open. Okay, so let's do that. So what does it mean to not be inside G hat? That means it has to fail one of these compatibility conditions. So that means there are two indices, beta and gamma, whatever they are, such that if you apply phi beta gamma to G beta, that's not G gamma. Okay. And what I want to do is I want to take this tuple and I want to find some open neighborhood of it disjoint from G hat. Okay. So what open neighborhood of that? Well, what you can do is let's look inside this big G beta, and an open set in that is, well, it's got the discrete topology, so you can pick just the singleton element G beta, and you look at the inverse image of that. So there are all the tuples H alpha such that H beta equals G beta. So that's a sub-basic open set. And then you can pick another sub-basic open set, all the tuples where H gamma equals G gamma. When you intersect the two, you get this U, which is an open set, all the tuples such as H beta equals G beta and H gamma equals G gamma. Okay. And since for all the tuples here, when you apply phi beta gamma to this H beta, that's G beta, it won't equal this G gamma by this thing here. Okay. So this will be disjoint from G hat, and also it contains this point here because G beta certainly satisfies this. Okay. So that's how you show that G hat is closed inside the product. Okay, all very well and good. So what do we do now? And this is the rather interesting thing. So one of the theorems that hopefully you learnt in your topology course, your general topology course, is Tikhonov's theorem, which tells you that any product of compact groups is compact. And this applies not just to finite products, it also applies to infinite products as well. So in this case, you have, since each of the G alphas is a finite set, okay, even with the discrete topology, it's still compact, and so that means the product of these is a compact topological space. And G hat is a closed subspace of the compact topological space, so it itself is compact. Okay, so that's rather nice. You have this compact topology, okay, on this profinite group. It naturally comes with how it is. Okay. Now I'll leave it as an exercise to show that the multiplication and the inverse are continuous. Basically because it's, what is the multiplication? It's just coordinate-wise multiplication, right? And coordinate-wise inverse. And in each coordinate, it's continuous because you have the discrete topology, okay? So that's the basic reason why. So let's go to the other part, which is to show that the open subgroups are precisely the closed subgroups of finite index. And the reason why I want to show you this is it shows a number of interesting techniques in the theory of topological groups, which if you haven't played around with, are rather fun actually. Okay, so we're going to start with H is an open subgroup of G hat. So the first thing that you can do, because it's a group of course, is that you can write this G hat as a union, a disjoint union of cosets. Now remember, you have a continuous multiplication. It's a topological group. So when you multiply by any group element, okay, it's going to send, it's going to be a continuous map. And in fact, since it's invertible, okay, the inverse is multiplied by G inverse, it's going to be a homeomorphism. So it'll send H, multiplication by G will send this open set H to the open coset GH. So all these cosets are open. Okay, if you have an open subgroup, all the cosets are also open. So this is actually an open cover. Okay, so that's an open cover. But this is also a partition. Okay. Now we're going to use the fact that G hat now is compact. So you have a compact topological space and you have an open cover, so you can find a finite subcover. But since all these cosets are disjoint, there is no subcover, okay, proper subcover, so you can't remove one of these open sets and still cover this. Okay, so basically the only finite subcover you can have is itself. So in other words, this is already a finite open cover. But what are the elements of this cover? They're just the cosets. So there's a finite number of cosets, so that means the index is finite. Okay, so that's rather nice. Okay, how are you using a mixture of continuity of group multiplication and also compactness here to get this result here. So I guess the other thing that you need to show is that this H is also closed. So that means the complement is open. But the complement is just a union of cosets. It's all the cosets other than H, right? So that means that's open, so that tells you it's closed. To get the converse result, that if you have a closed subset of finite index, you basically just reverse the argument. It's quite easy to see. Okay. So that's a rather wonderful fact about profinite groups. Okay, it's a compact topological group. Okay, and if you want to look at open subgroups of it, okay, they're just the closed subgroups of finite index. Okay, so I want to look a little bit more at this very important profinite group Z hat, because this will appear quite a bit in arithmetic. If you want to do Galois theory that's appropriate for arithmetic, it appears quite a lot. And this will also show you how it's quite an interesting topology, what's going on. So one thing that to note about this is that, and this is something that I want to emphasize, is that here it looks like when you put the discrete topology, it really doesn't contain much information. Okay, so once you have a discrete topology on things, okay, if everything's discrete, you think that, well, all maps are continuous anyway, so you're not going to get any information. Okay, but the funny thing is that once you have this product on here, okay, the product topology is no longer discrete. Okay, if you have an infinite number of sets here, topological spaces, okay, that is no longer discrete. And so you can have interesting topologies coming up. And one thing that I want to show you is this little result here, which sort of emphasizes this, and hopefully gives you a little bit more feel for what the Z hat is. So here we have the Z hat, okay. So firstly, it is, you can look at the element 1 inside Z hat. So what's the element 1 inside Z hat? So what you do is you need a tuple that's in every Z mod n, and in every Z mod n it's 1 plus the nz. Okay, so 1 plus nz, and the compatibility is holding because 1 plus nz does map to 1 plus mz for any n and any m. Okay, so that's the element 1, and so you can let it generate some sort of subgroup of this Z hat, and that's fine. Okay. And what's rather interesting is that, well, it's not going to be the whole of the Z hat. Okay, that's certainly true. So it's not a generator for Z hat, because Z hat is not a cyclic group, but it is a topological generator for this group, in the sense that you look at this group generated by 1, which is isomorphic to Z. If you look at the closure of this group, and since it's a topological group, the closure will be a group itself, then in fact you'll get the whole of Z hat. Okay, so that's rather interesting. So we say it's a topological generator. Okay. So the smallest closed set containing this group is going to be Z hat itself. And I don't want to go through the full reason why this is true, but let me give you the main reasons, and I wanted to just work a little bit more on some of the basic techniques that is involved when you want to study profinite groups. So firstly, when you have the Z hat, remember, when you have a product, you can always project onto one factor. And so if you have a subgroup of that, you can also project onto that factor. So that's what we'll do here. This Z hat, we can project onto the factor Z mod M, and we call the kernel of that map UM. Okay, so this is basically just, you have a tuple here, and you pick out the nth element here, which will be an element of Z mod M. And well, basically, this is going to be the inverse image of GM inside here. So this is a element inside here. It's a subset too, you can think of it that way, and it's an open subset. So this is going to be an open subset, and it's a kernel of a group homomorphism. Okay, so it's going to be an open subgroup. Okay, what is it? Cosets. The cosets are just going to be the inverse images of the other elements inside here. So they're also open subsets. So all the cosets of this UM are actually open sets. And just by the definition of the product topology, these cosets of UM, they form topological subbases. And what's rather interesting is that in this particular example, you have something special going on. If you try to intersect some of these, okay, then actually you'll get unions of cosets of possibly different UMs, okay? So that, and this follows from the Chinese remainder theorem, okay? So basically, if you saying that you're in some coset of U3, that means that you want basically all your numbers to have a certain congruence relation modulo 3. And if you want to be in a coset of U2, that means you want some congruence relation modulo 2, and then that you can reframe as some congruence relation modulo 6. Okay, so that's the basic idea that actually this topological basis, okay, subbasis rather, is actually a topological basis. Okay, so that's a topological basis, and so since every non-empty open set is a union of basic open sets, you just have to show that every one of these cosets intersects this group non-trivially. Okay, there's a non-empty intersection. So what's a coset? The coset is just a pi inverse of some element like this, so pi inverse of L plus mz, and you show that when you intersect it with 1, that's going to be non-empty, and that's very easy to see because what's inside here, okay, something that's inside here is just L itself. If you look at L times 1, okay, that's certainly inside here, and if you apply pi m to it, you will certainly get L plus mz, and that shows you this fact here, which gives you this rather nice result, finally proves this rather nice result, that 1 inside this Z hat is a topological generator. I hope you enjoyed this adventure in pure mathematics.